All right, I'll give you just a moment to read through it real quick if you hadn't had a chance to look through it. Hopefully, you have already this semester. All right, if you've had a chance to look at that, uh, let's think about the find statement here real quick. In this case, you're looking for a couple of things. One is so if you think about this, what's happening is you've got a like an IV bag that's got fluid in it hanging above the patient, and then the tubing that goes down, and then the needle stuck into various different veins in the subject, and uh, we're looking at, depending on which vein or which location, there's a different flow rate from this bag hanging at the same height, and they're asking uh, by being able to measure that flow rate to determine what the pressure is, the interstitial pressure for each IV location. And it's also asking for the resultant force. You're also being asked for the resultant force at each location on the catheter or the needle, the catheter needle, to maintain its uh, position. So now let's get a diagram here real quick. Grab. Think about what the system is that's going on here. So you can see this. I'm going to plug it into the here. So let's walk through, talk about this system here. So this is the IV bag up here, and then this is the tubing and the needle stuck into the patient here. And at this location up here, you're going to have some velocity inside this IV bag moving this way. And we're going to assume that this velocity is so small compared to this that we're going to assume it's zero because this diameter is so much bigger. You can imagine the IV bag compared to the diameter of the tubing. We're going to call this zero. But now there's a pressure here, and then here's the unit vector in this end of the system. And then you've got the unit vector, the velocity, and the pressure down here at the other end. So that's the system here. So now we're going to make some assumptions here. Let's go to those. Okay, so if this basically the system is this junction, that the transition from the IV bag to the tubing and the needle here going out. So this is got fluid entering from the rest of the IV bag going into this system uh, and then out. So this is an open system with material crossing system boundaries. You can see it's leaving the system down here at the bottom. It's going to be steady state. We're assuming that it's getting to this volumetric flow rate here and staying there. So this is going to be steady state. Also, we're going to assume, for purposes of being able to use the Bernoulli equation, that the fluid flow in this system is inviscid and it's an incompressible fluid. So now we're going to set up a basis. The basis in this case is going to be given in the problem statement here. It's we're basically going to do this problem 5 times, once for each of these numbers here. So let's take that information and we're going to put that in here. Oh, I need to actually type the numbers in here. Let's do that. V dot is going to be equal to a matrix. Maybe I can copy it from up here. Let's do it this way instead of typing this all. Oh. I may have to type it. V dot is equal to 23.6. So we need to put in a vector here. I'm going to put them all in at one time. Let's delete that. Okay. 23.6, 3, 16.5, 12.1, 8.8. These are all in mLs per minute. Now, we also need to put other given data here. So let's do that. First, we want the if you look here, I think the 22 gauge catheter here. You have to look that up. You can find that that's here. And then I'm going to do a definition of a unit here so that we can do it in terms of the given in the problem. Now we need to put I'm going to define our unit vectors here. So let's put in our unit vectors. So if you look at those unit vectors, you can see that this one is 1 in the y direction, and this is y in the negative x direction. So that's why it's y. The n1 is 1 in the y direction, and n2 is minus 1 in the x direction here.
Dr. Vernon?
Yep.
What is that in the MMHG? What is that equal sign?
That's a global equal.
Uh-huh.
So even if I use MMHG above, that will already be defined. So MathCAD goes through the document once and gets all the global equals, and then comes back to the top and goes again.
Okay, so how do you get that? How do you get it into your...
Yes. If you go here is if you type the if you actually go to operators, it's right here.
Okay.
Global definition,
Okay.
or you can put Control Shift tilde. And then that's just global, meaning that it goes through your document once in the same way from top to bottom, left to right, getting all the global assignments, and then it goes back up to the top and then actually does all the other calculations, having all these globals already defined.
So, okay, wait, sorry. So like you defined it right there, and like it'll impact things that are earlier in the document?
Correct. So like I could come up here
Okay.
above it and I could ask it
Okay.
does that make sense? Where normally
equals...
I can't go over here and say I can't ask what n is equal to because I didn't do a global definition.
Okay. Okay, cool.
Okay.
Thank you.
So sometimes it's nice to do a global definition. All right, let's delete that. All right, so now we've got our unit vector. We also are given a height in here, so let's put h is equal to, there was h1 and h2, so we'll put a position vector, h1 and h2, height of the two different. So I'm going to put a matrix or a vector in here that's got h1 and h2. That's going to be 1 meter and 0 meters. We'll call h2 down here at the bottom 0 meters, and the top it'll be 1 meter. So this bag, this intersection between the IV bag and the tubing is a meter above this needle position. So that's what that's saying. And then let's go to density. I think the densities are defined in here, right? The density of the tubing, and then there's density of fluid. So we've got two different densities that we can put in here. So I'm going to like this. Copy, put this over here. So I've got, this is the fluid density and this is the tubing density. All right. We also were given some pressures. So let's put a pressure at P1 is known. So P, and it's actually the 0 position is the top, is 1 atmosphere. And then the outer diameter, we have an inner diameter and an outer diameter. The inner diameter is here. There's also an outer diameter. We're going to need that for purposes of the body force to calculate the weight of the tubing so that we can get the body force. So OD in this case is 0.028 inches. That's a normal 22 gauge catheter. Let's do that in millimeters. Okay, so that's, I think that's all the data that I need. So now we're going to come down here and start to calculate. So if we calculate, first thing I'm going to do and calculate is figure out what are the equations I need. So if we're going to calculate, there's a couple of things we're looking for, right? That's going to be the pressure at P2, this P2, and for the resultant force. So that's two unknowns. We have to have at least two equations. So the first one is going to be the Bernoulli equation, as you can see from the assumptions that I made, that I'm probably going to use the Bernoulli equation. So the Bernoulli equation looks like this for the system here. We'll copy and put this in here. It's basically, it's the difference between the potential energy, kinetic energy, and pressure energy at the two locations, P1 and P2. So that's the first equation. So then the second equation is going to be the momentum equation. That's the one that you learned just last class period, and with flow through a system, an open system with flow and the momentum. And in fact, that's what the quiz is going to be over on Thursday. But that equation looks like this. Put this in here. So you got the momentum of the mass rate going in times the velocity going in. This is the velocity. And then the unit vector, the minus of the unit vector, because if you look at the velocity and the unit vector have opposite directions, so you need the negative of the unit vector to give it the direction. The V1 is the magnitude, and then M1 is the mass flow rate. That gives you the momentum of the fluid coming into the system here. And then you have the momentum of the fluid here leaving the system at this end, and you can see that N2 and V2 have the same direction. So when you multiply by the unit vector here, you multiply by a positive unit vector times the magnitude of the velocity, because that gives you the vector, velocity vector coming out of this tube. Now you can imagine if this needle were not horizontal, maybe it was at an angle, then you could use a unit vector that was a length of 1 that was at that angle, and maybe that's something that would be interesting to see. It'd be nice if you gave me some problems where there's an angle there, so you have multiple components in this unit vector. Then this momentum equation has the pressure forces here due to the pressure, and you'll see that the pressure is opposite the unit vector in both ends. So that's why you have a negative here instead of a positive, is because it's really plus the negative unit vector times pressure and area. So pressure times area is force, and then multiplied by the unit vector gives you direction, but the negative unit gives you the opposite direction. So the pressure is going the opposite direction of the unit vectors. And then you got the pressure force at 1 and 2 in this equation. And then the body force, we need to be able to calculate the body force. That's going to be the pressure on this whole thing due to the weight of the system acting at the center of mass. And then the resultant force is the force on this system that's keeping it in place. So let's start calculating now then. So that's the setup anyway. So some of the things that you need to think about in calculating these now is you're going to need to calculate the area. But you have the diameters, and you have the unit vectors, you have the pressure at P0. You don't have this pressure here, P1, or this one, P1. Go look at this equation, though. You should have everything else. You've got the, if we're assuming that this velocity here is 0, then that cancels this velocity here. And the reason why we can assume that that's 0, now you could say it's not 0, and if determine what maybe it's 10 centimeters here is the diameter of an IV bag, and then calculate what the velocity is based on this flow rate at 10 centimeters, you'll find that it's very close to 0, but it might not be a bad idea to actually calculate that. So do a calculation on V1 from this data based on this area here. Remember, the volumetric flow rate is a meter cubed per second. How do you find the velocity? You divide by area, right? And that will cancel 2 of these meters, and you'll just have meters per second. So you find the area of this interface here and this here, and that'll give you the 2 velocities, V1 and V2. This one will be very close to 0, but it would be interesting if you guys can let me know how close to 0 that was. And then after you've used this equation to solve for pressure 1, then you can plug it into here and use this to solve for this FR. How do you find FB? That's probably the other big thing that you need to be able to set up here. And the equation, I'll show you the equation and we'll walk through and talk about where this equation, what it means. I haven't calculated the area, so that's errored out, but you just calculate the area from these diameters. So if you think about it, it's basically the area times the height. So this tubing, the force on the tubing is not going to have the weight of the bag. So I'm going to multiply this height by the area. So basically height times area gives you the volume of this cylinder. That's the area, and then multiply that by the density of the fluid, and that's the weight of the fluid inside this tube. And then this one here, you're taking the density of the polymer now, so of the plastic tubing, of the plastic part of the tubing. So you're taking the area of the tubing and the area of the fluid and subtracting out the fluid. So now you've got a hollow cylinder, which is just the wall of plastic, and multiplying it by the height and the density. So now you've got the weight of the plastic and the weight of the fluid, and you add those together, and you get the body force acting down. No, the area you can calculate from these. Area 1 is from this diameter, and area 2 you calculate from this diameter.
Okay.
So
So
area could be calculated as simply as this. Let me we go like this. It's basically right. The first area is going to be the inner diameter squared over 2 pi. So that's the area of the fluid inside of the tubing. You multiply by the height. Now you've got the volume. So this is the volume of the fluid times its density. That's the weight of that's basically the weight, the force of the fluid, the gravity force of the fluid. Then this second one here is going to be, now I must have changed the origin on the one I copied from, but the second area is the area of from the outside of the tube. So this one's the inside of the tubing, so that's the area of the fluid. This is the outside of the tubing, so it's the area of the fluid plus the plastic. So if you want to get the volume of the plastic, then you subtract off the area, the volume. This is the volume of the fluid, this area 1, and this other area is the times the H is the volume of all the way out to the outside of the tube. And if you subtract the fluid from the inside, then you basically have the volume of that shell of tubing that's on the outside of it. Does that make sense? You're solving for this FR. Because
okay.
the fine statement is, what's the resultant force? Before you're going to rearrange this equation here and solve it for FR. But you can't do that till you've already solved F. So before I solved this up here, I'm going to rearrange it. So I'm going to get, in the end, it's going to look like this rearranged. Like that. You're going to rearrange that second equation. This first one, you're going to rearrange for like this. Let me copy this. So this first equation is going to get rearranged to look like that. So you're solving for P2. I'm sorry, it's P2 on this first one, right? Because P1 is given as 1 atmosphere up here. So you're solving for P2 in that first equation. And then you're taking that P2 and plugging it into here, solving for the body force here, plugging it into here. And then everything else, then you have to solve for your velocities by taking the volumetric flow rate here, dividing by this inner area,